for the next task. Net force, multiple forces. All right, so what do we do when we have multiple forces acting, right? So you got the weight, you got the push, you got the resistance. So how do we figure out what the net force is? So net force is the sum total of all forces acting on a system. All right, so it means that the direction is going to matter, magnitude is going to matter, and you can sum up the forces along the x and the y direction, as well as z direction. So net force means sum of all forces along the x direction, and the net force is going to be responsible for the acceleration. That's what it means. Now, the net force is just summation of all the forces. In this case, you got F1 to the right, F2 to the left. So it's going to give you 5 pounds. Yeah, this is a real simple illustration of what a net force is. So it's just subtotal of all forces. All right, so in terms of problems, for college physics as well as university physics, I'm going to focus on the same problem, except the university physics solution is going to be a lot more algebraic, meaning that you will have to do this stuff literally just symbolically. All right, so 90% of the work is going to be symbolic. College physics, just pick the formula, do a little bit of algebra, and plug the numbers in. College physics is not mathematically as rigorous as university physics is. College physics students are not going into engineering, so it's exactly the same problem, except the solution is a little bit easier. All right, so what do we have? We got the car coming to a stop due to the engine cutting out. All right, so what do we know? The car is already moving from left to right at this speed. And then as soon as the engine cuts off, there's friction, there's tremendous amount of friction acting on the car. So the motion is in the forward direction. It's already moving at like 74, 75 miles per hour. And then the frictional force kicks in. As a result, the vehicle is going to come to a stop under the influence of friction within this distance and within that time period. So the initial speed to final speed is stopping in the forward direction within this time period. All right, so I'm listing everything first. All right, so it'll come to a stop within 1,000 feet. I'm not sure if I'm going to give you the distance on the task. And this is the amount of friction acting on it. All right, let's just do it this way regardless. All right, determine the net force acting on the car. So which means that sum up all the forces. So what we have, we got only one force acting on the car, so it's the frictional force. All right, so determine the acceleration and determine the time it takes for it to come to a stop. All right, so we need to do the conversions, obviously, that's the first thing. Feet to meters. Pounds to newtons. All right, so now the net force. So these are the formulas available for us. These are the ones I'm focusing on. All right, so the net force is summation of all forces acting on a system. So there's only one force acting. It's the frictional force, right? So the net force is the same as the frictional force. All right, so that's going to be 8,000, not 800. So I'll make a correction at some point. It's going to be 8,000. All right, so the next one is what causes the acceleration? Net force does. So net force is responsible for the acceleration. Boom, 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 boom. All right, once again, it's going to be 8,000, not 800. So we'll make the correction. So the mass of the vehicle is given, that's 2,000. All right, so I made the correction already, made the correction there. So that's the acceleration of the vehicle. It's going to be negative, it's slowing down. And then what's the time it takes for it to come to a stop? All right, so now we have to make a decision. For time, either focus on this formula or this one or this one. All right, those are the formulas that we can focus on. All right, so you can pick this one if you assume that the acceleration is variable. If you assume that this is a jerking motion, then use this one. If you assume that the acceleration is constant, you got to use one of these. So if you make the assumption that the acceleration is variable, all right, these formulas won't be available. All right, and if you make the assumption that the acceleration is constant, this formula is not available. It's an either or supposition at this point. All right, you cannot use this formula in conjunction with those, and you cannot use these formulas in conjunction with that. So either or. So I'm gonna make a decision that the acceleration, the force is constant, the acceleration is constant. So I can use one of these formulas. So the one that I would get to use is probably the last one. All right, so that's the one I'm using because that's the easiest one to use. All right, so final speed is 0. And then solve for time, and then we're done. Plug the numbers in. 8.2 seconds. All right. All right, so college physics students are allowed to break it down and do it step by step, in a step-by-step fashion. All right, that's how it is done. All right, so now the same thing for university students. Everything is the same except I won't give you the distance because you don't need it. You can figure that out. All right, so for my university physics student, how does it need to be done? All right, so a couple of things. Always have a force diagram. All right, this is also true for college students, college physics students. Always have a force diagram because you're dealing with vectors at this point. Force to the left, frictional force. Motion is in the forward direction. All right, so we got the distance. We got the time. What else? All right, I'm just going to copy the information from the previous one. And then figure out the time. All right, so which means that you will get to do this in one single step, in a sense that, you know, it's one continuous algebra. All right, so the way I'm doing it is my way of doing it. You don't have to do it my way. Just you do it any way you want. I don't care. Just show work. And then explain and justify. All right, with this test, you guys will have to start justifying. My way of doing it is just go after T. All right, so time, these three formulas got time in it. So I'm just going to pick and choose the one that I want to use. And I'm willing to do a bit of a trial and error at this point. So I'm going to give you guys, with this test, you're getting 45 minutes. So you'll have enough time to goof around if that's what you want to do. All right, I'm thinking that I'm not going to use this because it's going to give you a variable acceleration. So that's really going to limit my options on the test in case I need to do more than just looking for time. All right, I'm just going to assume that the acceleration is constant. So it gives me three formulas that I can play with. So this is pretty rich here. So, but the assumption is the acceleration is constant. So which means that the friction is constant. So I'm thinking I can either use this one because X is given. I'm not going to give you X on the test. So just remember that. All right. So because this is completely not needed. And X is given, I can use this. And then I can also use this because initial to final speeds are given. The acceleration is something that I can figure out. So it's not, you know. All right. So it'll work itself out at some point. All right. So I decide that I'm going to use this one. All right. So I can directly isolate T at this point. This formula is going to have two unknowns, which I'm okay with. Two unknowns means two equations. All right, so I got my T. Now I need to figure out what my A is not given. It's not going to be given to you. I know that the acceleration is caused by the net force. All right, so which requires an interpretation. I don't use the formula as is. All right, this is more of a symbolic. This is more of a summary statement. This is the net force formula. Net force is what causes acceleration. That's what it means. All right, so which means that you have to figure out what the net force is. So the net force is what causes acceleration. So that's the reason why when I'm down here, I say, all right, so the net force is what causes acceleration on the X direction. I know what the net force is because I got my schematic. All right. So there's only one force acting on this vehicle. So the net force is going to be the frictional force, right? Opposing motion. So this net force becomes the frictional force. So back substitution right here. And now I can solve for A. And this gets substituted into that formula. And that's it. All right, so negative divided by negative is positive. Denominator of a denominator is a numerator, so this is going to go up. And that's the final formula. All right, so do I have numbers for everything? All right, that's the next step. All right, so if I know the mass, I'm good. If I know the initial speed, this is good. If I know the frictional force, this is good. So I think we got numbers for everything. All right, so we got numbers for everything. We are good to go. So you plug the numbers in and you're going to end up getting the same answer as before. All right, so mathematically, college physics and university physics, I'm going to give you a problem similar to this, okay? Except, let me explain, let me add on to it. All right, I'm not going to give you the distance in either case because I can ask you the distance, right? All right, so distance is not going to be given. So whatever it is, now that you guys know how to do it for time, learn to do it for, now that you know how to do it for time, do the same thing for distance as you're getting ready for the test. Know how to isolate X for this one. So mathematically, this is the only one which is interesting. If you can handle this, obviously this is good enough. And then let's take a look at the forces on the y direction. So the weight is the gravitational force acting on you. All right. Force of gravity. All right, so the apple falls and accelerates. Acceleration is caused by a force in the same direction. So this makes gravity or force. A falling object is accelerated at this rate, at a rate of g. So mass times the acceleration due to gravity is going to give you a weight. So this force of gravity becomes your own weight. That's what it means. All right, so falling object is going to accelerate at a constant rate until it reaches some kind of a surface. At that point, it comes to a stop. Stops accelerating. The reason why it stops accelerating is because net force acting on it is zero. Net force acting on it is zero because it now is also experiencing a surface force, right? So this surface force is a reaction force to inner force applied to a surface. It's called normal force because it's normal to the surface. Normal does not mean normal versus abnormal. It's a mathematical term that simply means it's perpendicular to the surface. So that's what it means. All right, so it's a reaction force and inner force applied to a surface, in essence. All right, if you're getting your normal force reading from a scale, it's known as the apparent weight, or the scale reading. All right, the only thing which is interesting here, aside from the terminology, is the mathematical modeling of it. All right, so this is more important for engineering students, the university students, and the college physics students. College physics students, as long as you get the concept, you guys are good to go. All right. For university physics students, because you will do tons of this sort of stuff in engineering classes. So I just want to make sure that we're making a nice, smooth transition into the land of mathematics here. So sum up all the forces on the y direction. All right, so net force is zero. The reason is because there's no acceleration. All right, and then you can just sum up the forces. All right, so n is in the upward direction, w is in the downward direction. N is up, w is down. So when you sum up the forces, n is going to be positive, upward forces are positive, downward forces are negative. So n is positive, w is negative. And that's going to add up to zero because, like I said, there's no acceleration on the y direction. So which means that your n and w will be the same. N is a reaction force to w. So that's the reason why this is known as apparent weight. Normal force is also known as the apparent weight if it's a reaction force to the weight applied to a surface. All right, that's it. So the apparent weight is your normal force reading from a scale. All right, why is it called the apparent weight? It's called the apparent weight because that happens to be the way your weight appears according to the scale. All right, so what that implies is your apparent weight can be different from your actual weight, depending upon the accuracy of the scale, obviously, depending upon whether or not you put 1 foot on the floor, and you can put your arm on a countertop for you. So it's depending upon what's going on, depending upon the shenanigans, the weight reading that you will get from the scale is going to vary. That's what it means. Also, the scale is going to be sensitive to the acceleration. Take a scale into an elevator on top of it, and if the elevator is accelerating in the downward direction, you will appear to weigh less. If the elevator is accelerating in the upward direction, you will appear to weigh more. And if there's no acceleration, there's no change in weight. All right, so when the acceleration is in the downward direction, you will feel lighter. In the upward direction, you will feel heavier. When there's no acceleration, there's no change in weight. All right, so let's do a review up to this point. Weight is going to represent the gravitational force acting. All right, and so weight differs from mass. Weight is the force of gravity acting on the mass, and mass is the measure of inertia. Normal force is a reaction force to inner force applied to the surface. In this case, the force applied to the surface is through weight via weight. So the reaction force is the normal force. So the normal force reading from a scale is known as the apparent weight. Apparent weight can be different. Obviously, you can shift some of the weight onto a different surface. It's also going to be acceleration sensitive. All right, so if the acceleration is in the downward direction, you will feel lighter. In the upward direction, you will feel heavier. And if the elevator is moving at constant speed, no change in weight, it's going to feel the same. All right, so this derivation is important. Once again, it's more important for university physics students from a mathematical modeling perspective. The college students just understand how it is done a little bit. I'm not going to ask you to do something like this on a task. Maybe in the multiple choice section, but that's it. This is once again straightforward though. All right, so center of mass to center of gravity. Scale is right here. Actual weight, apparent weight, normal force. All right, so acceleration could be up, down, or no acceleration. And sum of the forces, n is up, w is down. All right, so the net force is going to cause the acceleration. Acceleration could be up, if that's the case, positive. It could be down, if that's the case, it's negative, and that's it. So what is the apparent weight of a person inside an elevator when the elevator is either accelerating up, down, or no acceleration? All right, so solve for n. That's it. All right, so we came up with a summary statement here. So let's interpret this, and then expand on it. So what this means is this says, here's your actual weight. This is how much you really weigh. All right. And here's the reading that you will get from a scale, depending upon what the acceleration is. All right. So this says if you're accelerating up, all right, so your acceleration times your mass is going to be added to your actual weight. You will feel heavier. If the elevator is accelerating in the downward direction, your acceleration times your mass is going to be subtracted from your weight. You will feel lighter. No acceleration, no change in weight. That's it. All right. This is a beautiful mathematical model. All right. It's very to the point. I like that. So if you're accelerating in that direction, you will feel heavier. Got it? Because acceleration times your mass is added to your weight. If the acceleration is in the downward direction, you will feel lighter because your acceleration times your mass will be subtracted from your weight. And if there's no acceleration, no change in weight, beautiful. All right, so all this, we go through all this, not only to get a really good understanding of what goes on from a mathematical perspective, but also this stuff is important because there's a mind twister coming up. It's related to the observation that we had in the beginning of the semester. So the cable snaps, you're inside an elevator, standing on a scale. What's the scale rating at that moment? So the moment the cable snaps, so that's important. The moment the cable snaps, how much do you appear to weigh according to the scale? All right. So the moment the cable snaps, it's 3 pounds. All right. So number one, acceleration is in the downward direction. So intuitively, you know, you will weigh less. So the question is how much? So here's your weight mg, and then this acceleration is going to be the same as g. So which means that this acceleration will be the same as g. So mg minus mg is going to be 0. So as soon as you find yourself in a falling elevator, you will feel weightless. All right. So this is crucial to obviously the next lecture and the following lectures. This is a good discovery right there. All right. Now let's just go in and then fill in the blanks because we can quite explain why you would feel lighter or heavier or no change in weight. That was just an observation. And then based upon the observations, we came up with a mathematical model and then we stopped at that point. Okay. So that's not quite 100% physics up to that point. Now we have to explain why you will feel lighter. So elevator acceleration in the downward direction. All right, so get it, you will feel lighter. Question is why? Acceleration is up, you will feel heavier. Why? No acceleration, no change in weight. Why? And then let's do 24. Let's make an attempt at 24. So when the elevator starts to move from rest in the downward direction, you'll feel lighter. All right, why? Because when the acceleration is in the downward direction, you got mass. All right, so what is mass? Mass means the measure of inertia, right? In essence, that's what the scale is trying to measure. All right, it's the measure of inertia, meaning that it's the measure of tendency to retain initial motion. And because the body wants to retain its initial motion, it's going to resist change of motion. So by the amount of mass that you have, you will resist the change of motion. All right, so here, elevator is accelerating, the motion is changing, and your body is going to resist that change of motion. All right, that resistance to change of motion is going to appear as the deficit in your weight on the scale. All right, that's what happens. Likewise, when the elevator starts to move from rest in the upward direction, you'll feel heavier because guess what? You got mass. Your body is not going to want to move. It's got inertia, so the elevator needs to overcome that tendency, and your body's going to offer resistance. So that the amount of resistance that your body offers in change of motion is going to appear as the extra weight you see on the scale. So once again, the answer is inertia. When the elevator is moving at a constant speed, there's no change of motion. Your mass is simply maintaining its initial motion, so there's no resistance at that point to change of motion. As a result, the reading you get from a scale is identical to your actual weight. 24 is straightforward. Now it is straightforward because we kind of covered this like from every single angle possible. And so now the elevator is slowing down to a stop while it's moving in the downward direction, right? So do you feel heavier, lighter, about the same? And you know the answer. You will feel heavier. So why? Inertia. Your body is going to want to maintain that initial motion. So it's simply going to offer resistance to change of motion. And that resistance to change of motion is what appears as the extra weight on a scale. All right, so that's conceptually, that's it. Mathematically, the emphasis is going to be on the net force. All right, on the net force. And the complexity-wise, the only one which is really interesting is a skidding motion. If you can do that mathematically, that's beautiful. Then you're ready for the next step, obviously. All right, so net force is where we are at. And then make sure you do the force diagrams. And then now, because we got more formulas with each passing week, more like it. Make sure that you identify when you're identifying the formula. Just explain why you're picking it. The formula that you pick needs to be kind of justified when you have like tons of formulas all over the place. All right, so multiple forces, the surface friction. This is not surface friction yet, but multiple forces. Good. The next one was the air friction, so we focus on this one. All right, so we will have a few conceptual questions from this one. So everything related to the elevator, the conclusions, and the justifications are test questions.
I have a quick question.
Yeah, go ahead.
So is this test only over net force or completely chapter 4?
No, this is only on net force stuff. It's only on the stuff that I'm covering. The multiple choice section may have questions from the stuff that we covered. It's more comprehensive usually, but the written portion of the test is only related to stuff that I'm just going over right now. In physics, everything is related to everything else. So just you have to kind of remember what we did previously. All right, so air friction. I put the emphasis on this one because this is a really amazing mind twister. This was literally, when I saw this question as a freshman, I fell in love with physics because I just couldn't figure this out. I couldn't figure this out. This was just so bizarre. It's from an engineering physics book, Halliday and Rasnick. This was a lead-in observation. I read it. I said, oh, I can't even fathom how this could be possible. So longer the distance of fall is, the better the cats will do. Right? It's a beautiful mind twister. It's a beautiful mind twister. It just so happens the answer is related to air friction. Who knew? All right, so it's related to air friction. So air friction is going to be related to the amount of air friction that you experience. It's going to be related to air density. It's going to be related to exposed surface area. Speed of the falling object is going to matter in terms of the air friction that you're experiencing. And also, it's going to be related to conditions of the air mass. All right, so those are the contributing factors. So object is falling. It's falling because gravity is acting on it, so that's the weight. And there's going to be a frictional force acting on it, so that's your air friction. And it's going to be moving at a given speed, whatever the speed is. I call it the terminal speed, but that's just too early to call it a terminal speed at that point, but we'll call it a terminal speed at some point. So friction is going to be directly proportional to air density, the exposed surface area, speed of the falling object, and then lastly, the conditions of the air mass. That's it. All right, so, and then we'll just, every one of them is going to have a fractional contribution, so which means that you get to multiply them all with each other just to come up with some kind of an empirical or observation formula. And then you make some adjustments in a laboratory. All right, so if we have any physics students, I'm not sure we do right now. All right, terminal velocity or air friction depends on a bunch of other things mathematically in terms of modeling. This is one way of modeling it for special cases for relatively small objects. The formulas may vary. For those of you guys who are physics students or majoring in physics, you will get to take the 300 level mechanics course where you will see how this usually changes. All right, so this is fundamentals of physics. I'm just going to go with this formula. All right, so the formula gets a little bit adjusted. So the next thing I need to do is check to see what happens, because the faster you go, the larger the frictional force is going to become. And the frictional force is going to become equal to the weight at some point. Under the circumstances, the net force acting is going to be 0. And which means that there's not going to be acceleration. So which means that this object is going to keep on falling at a terminal velocity, one constant speed, which is known as a terminal velocity. So when the frictional force becomes equal to the weight, no acceleration, the object is falling at a constant speed. All right, otherwise known as the terminal velocity. All right, so which means that you can take the frictional force and replace it with the weight, and then I call this the terminal velocity. So that's going to give us a relationship between how much something weighs and its terminal velocity. So that's what we're exploring. And then we finish up with mathematics, isolate the terminal velocity on the left-hand side, and draw our conclusions. So heavier objects will fall faster. We knew that. And heavier objects will fall faster. And what else? We also know that the larger the exposed surface area is, the smaller the terminal velocity is. So we got these proportionalities. All right.
12,000 feet above.
All right, so we will have a bunch of questions, conceptual questions from this.
The Earth, then suddenly a parachute that doesn't work. It's a virtual freefall, all recorded by then 27-year-old Eric Johnson's own helmet cam. It begins when Eric's main parachute deploys, and for reasons unknown, his backup chute opens too, a mishap with serious consequences. Watch as suddenly the two chutes entangle, and the equipment meant to break his fall is rendered useless. His fate seems certain. As the doomed diver spins out of control, he barely misses power lines and the asphalt of a road. Finally, he crash lands, and nobody can believe what happens next.
Thank God! I lived!
The skydiver lived.
I think it was probably luck more than anything.
That's for sure. Eric might just be one of the luckiest guys alive, and even he can't figure out how he cheated death.
I had that feeling the whole way down. I was like, this is not survivable. There's no way.
As an experienced skydiver with more than 500 jumps under his belt, Eric realized at 1,500 feet off the ground that he hadn't opened his chute, a full 1,000 feet later than it should have deployed. Eric knew he was in trouble, but concentrated on saving himself.
Panicking does you absolutely no good. So I didn't panic. I tried to handle it.
Eric broke his fall by letting his body go limp.
When I hit the ground, I hit like this.
And apparently the brush with death wasn't enough to keep him down. He continues to skydive.
As of today, I would tell you I probably will never stop. But who knows?
Spoken like a true survivor.
He is absolutely nuts. But true to his word, Eric has made hundreds of jumps since his accident, and this man who bravely faced death plans to help keep people alive. He's a medical student.
All right, so how do you survive the impact? All right, so his parachute got tangled up. Ideally, he wants to be falling around 15 to 20 miles per hour, except because the parachute got tangled up, his exposed surface area is a little bit compromised, right? So he's probably going around 50 miles per hour. All right, so can you survive impact at 50 miles per hour? Answer to that question is, depends on the acceleration, guys. If the acceleration is survivable, anything is survivable. It's not the speed you have to worry about. You have to worry about the acceleration. The acceleration is survivable, it is survivable. And acceleration depends on the impact time. So depending upon what you hit is gonna matter, right? So right at this point, he could either hit grass or he could hit asphalt, right? So hitting asphalt is kind of tricky. You can still survive that, but you need to generate a lot of impact time. Just about the only place where you can generate the impact time is going to be through your body, which means that you have to break quite a few bones. Or you can land on grass. Grass is going to give, which means that it's going to give you a large enough impact time. Guess what? Look, this is the difference between breaking bones and not breaking bones. All right, you land here, definitely it'll be survivable if you can break the right amount of bones. If you land here, yeah, I mean, you can survive even without breaking bones. So lands on grass. All right, so that's luck. He lands on grass. All right, so that increases the impact time. And then he does a few other things. He relaxes his muscles. Okay, so with relaxed muscles, that increases the impact time further. On top of that, he does another thing which is extremely smart. He gets his body parallel to the ground. Why does that matter? It does matter. Why? Because you take the impact force and disperse it onto a much larger surface area. In doing so, you reduce the pressure. So it's a combination of all those three things. He was able to increase the impact time by landing on grass. I don't know how much of it was intentional. He relaxed his muscles, that increased the impact time. On top of that, he got his body parallel to the ground. In doing so, he was able to disperse the impact force. And this whole ordeal became survivable without any injuries as a result. All right, so that's what happened. Now we have an understanding of what's going on in terms of what's survivable and what's not. Now we're focusing on the falling cat. All right, so this is the book Held in Investing, and this is literally, I just copied this now verbatim. This was the thing that I couldn't figure out. And then later on they called this the high rise syndrome, because it's happening quite often. And eventually they noticed that the cat's falling longer than 70 feet would be doing better than the cat's falling shorter than 70 feet. And obviously it's an investigation. All right, so it's all about the terminal velocity, which depends on the weight. Cats don't weigh as much. 6 to 12, 14, maybe about 16 pounds, which means that their terminal velocities will vary from 45 miles per hour to 60 miles per hour. And you saw what happened to the guy hitting the ground at 50 miles per hour. Even that guy survived. The guy's not even a cat, right? So what's going on here? So here's a cat falling from the top of the stairs tower. Here's a cat falling shorter distance. I'll make this less than 70 feet. All right, so is it so happens it takes 70 feet for a cat to reach its terminal velocity? This could be a cat which is 6 to 8 pounds, 45 miles per hour. And once the cat reaches its terminal velocity, all the way down, it's going to be 45. And the cat is going to hit this ground. This is a cat falling less than 70 feet. And it hasn't reached its terminal velocity yet. So it's moving slower than its terminal velocity. So that's 35 miles per hour. All right, so the cat falling from the top of the stairs tower is still moving faster. Yet this cat is going to do better. Why? The reason is because the muscles are relaxed. Once you reach your terminal velocity, you stop accelerating. So the sensation of falling gets replaced with the sensation of floating. That's it. If it feels like you're floating, then obviously the muscles are relaxed. This cat is still accelerating, so the muscles are much more tense. All right, so you get the impact time from your muscles in either scenario because the cat's got extra muscles. If the muscles are tense, it shortens the impact time. If the muscles are relaxed, it increases the impact time. So acceleration is inversely related to the impact time. So if you increase the impact time, the acceleration is going to be less. And guess what? With relaxed muscles, the acceleration is actually smaller because the impact time is larger. As a result, the cat survives the ordeal, and that's it on this task. From a multiple choice perspective, just know how to do these. I probably gave you guys my solutions for these. And you should be able to find the solutions for either class just go to class materials, open this up, college physics. Yeah, so the stuff is here. The stuff, the problem number 1 that I was showing you, solution is here. Problem number 2, not every single solution there, but you will be able to find most of them. And sometimes the numbers are different. All right, and just, I mean, the problem numbers are different, but the solutions will match something there, depending on which class you're taking. And this was problem number 8. This is the one that we just went through. So for college physics students, just focus on this. For university physics students, this is the stuff to focus on. Except I want you to redo this problem for X instead of T, either way. So the forces on the Y direction, we got a bunch of examples here. All right, so we have this is the acceleration of 2 falling skydivers, mass 132 kilograms, and equal to the 1/4 of their weight. All right, so the mass is given, so it's 132 kilograms. And the weight, air resistance is given 1/4 of their weight. So it's going to be 1/4 of their weight, and then figure out the acceleration. All right, the first thing I'm going to do is I'm going to do a force diagram. All right, and identify the forces. So they got weight, which is mg, and then they got the frictional force opposing the motion. And so the frictional force is given 1/4 or whatever. So the question is, what is the acceleration? So this thing is accelerating in the downward direction. So what is this acceleration? All right, so that's what we're trying to figure out. All right, so I don't have any conversions, so I'm just gonna start setting up the math at this point. So what I'm going to do is I'm just going to sum up all the forces on the Y direction. All right, so frictional force is up, and the W is down, and then I'm just gonna, the acceleration is also pointing in the downward direction. So I'm just gonna, let me just try this. I'm just gonna keep it pointing in the downward direction. All right, so F is gonna be in the upward direction, W is gonna be in the downward direction, the acceleration is gonna be in the downward direction. So I'm just gonna keep it like that just for now, and then see what happens. All right, so I'm gonna rewrite this. So this is gonna be W, and then isolate A. This is gonna be F minus W. And let me just move the negative to the left just for now. All right, it makes sense. All right, that's it. All right, so what do we know? All right, so we know that the frictional force is the same as W, 4 times larger. All right, so I'll do a back substitution. I'm keeping the negative M here. And so they need to have common denominator, right? So multiply this by 4, divide this by 4. And it's going to give us, all right, so this is going to give us, what is it, -3 times W divided by 4 M. All right, so I made a slight change. So negative divided by negative. This is divided by negative. It's going to be positive. So we got 3 times W divided by 4M. And then we know that this W is the same as mg. All right, so we do a back substitution. And then we got some common terms, which will cancel. So the acceleration is going to be 3/4 over g. All right, so if G is roughly about 10, so what do you got? So it's going to be about 7.5. I'm just going to work on less meters per second squared. All right, guys, this is an example of how you would do a problem like this. All right, so the mass at the end didn't really matter. It got canceled out. All right, so this is a way of solving a problem. All right, so this problem, despite the fact that the numbers are different, is the same as this problem. All right, so it comes out the same way. It's exactly the same as this one. All right. All right, so this is it.